Then now we have this covariant derivatives. We can do other derive other formula that we used before, in our vector calculus, except that now using all this language. The gradient is trivial. I think we write down that as 4.6 dB, basically a derivative of a scalar with respect to coordinate, and that one is trivial. So the divergence is the next one. We can work with it now. I think we are okay with other things. We have all the formula. That doesn't matter. We'll just look that up later. Okay, so once we have this covariant derivative, we can now talk about the divergence. I mean, the process is straightforward, except that you want to write a certain form that would involve a relation that might be a little difficult to see, but we'll just move on to see whether you can understand that. So just using the definition. So this is like a gradient, but with a contrarian basis. So epsilon j partial q j. Right. This is because the derivative with respect to the contrarian coordinate. So when you take a derivative, become covariant. So you need to contract the contrarian basis. So that's the operator. But then the vector itself has basis also. So you use covariant basis. So your contrarian component that actually this is another index I, and then contract with a covariant basis. Right, and so that's that. So that one is just basically this one. That's what it's basically, right? So it's epsilon j, and then just copy that. So this component is just this one. So it's that we can use k because we haven't used k yet. So possibly k. J mu, and then epsilon. Okay, I missed this. Oh yeah, I have it. That's fine. So this for housing is this one. This one has this one. So first term and then the second term, and multiplied by epsilon k is the whole thing multiplied by epsilon I. Where do I get I? I. Oh yeah. I use k here, so this is k is I. I'm not comparing the same thing. So this is I, this is k, this is I. So k changed to I, right? Epsilon A. Okay. Now this is like a dot product between j and I. I think the text missing a dot product. Yeah, that's it. That actually that's a dot product. And then you use the fact that countervariant basis and covariant basis are orthogonal. So this becomes a conical delta, and it's delta ji, right? And then you can sum over either one of them. Let's just write one more line. So, mu j mu delta j, right? And you can now either sum over I or sum over j. If you sum over j, then this becomes vi also qki, except that you need to pay attention that this notation means sum also, because this is from a contraction, right? In this, the whole thing is some contracting both I and j, sum over I, sum over j. So once you use the sum over j, you still need the sum over I. So although you write it like that, this is not, this, there's also a sum. This is still a repeated index, a superscript and a subscript. This means a sum. Okay, so this is the first term, and the second term is the same. Mu, gamma, I, mu. Now we don't need the bracket. Right, that would be, yeah, that would be equation 4.65, except your technique is k instead of mu. Doesn't matter, this is a sum. Okay, and then again, this is also sum, although it's in the same quantity, gamma, the Christopher symbol, so but you sum over this superscript with one of the subscript also. All right, so that's the divergency. And now, of course, you can just stop here and then just use whatever this Christopher symbol that you calculate and find your divergency this way. But if you want to write it in another form, the text will provide another way to write it. And that is basically many authors write it that way. Actually try this to understand why they can do that. It's basically working out this object, this using what we have here, right? So this gamma I, using a textbook negation I k is now basically it's the same thing here, but you contract with a countervariant matrix. So this is to keep an I here and using another index m, and just copy this string in here. So you have 1/2, and now you need to be a little careful because this is I, both are I, right? So there's two of them are I, so one of them is I, and this is this guy, the superscript is coming from contracting the second slot, this one, with countervariant metric tensor, right? So K becomes a I also. So you have K becomes something you contract, and then what we're using is M here. So it's partial GIM. The K becomes M. Partial Q. And the rest is we only have K. We don't have J. So the two indexes I and K is not I and J. So J becomes K. So K. And then the second one is similar. This J. Let's just follow your textbook. It would be minus. G. Right. Wait, that that that's too many indices. If you cannot follow, we need to write one more step. Because we want to sum over this guy, so we want to write it. Uh, okay. This is what I do. Okay, and then later on changing J to K. Right. And then this is coming from this is Christopher's multiplied by counter-variant basis. So I and M with changing M to the contracting. No, contracting the this is contracting one of them because you want to change that. These are all subscript, right? You want to change. No, you want to contract with the last one, right? So this is 4.62. So you want to sum over NK. You want to sum over this index. So sum the M, and obviously one of them. The other two are the order doesn't matter. One would be I. The other would be the um, this. The other two is the indices of the Christopher symbol. Once you contract that, so one of them is in I is in here, so J and K is in here. It take a while to figure out how to write it. Okay, that's more like it. You contract the second slot with the index of the contravariant matrix, and then the rest of these two subscript keep in here. Okay, so now you can write this according to this definition or this formula. So it's comparing. So IJK becomes a JKM. So J and K become N. J become K. And the second are basically interchanging J and K. This right. It's a KM. So J. And the third one is using these two as the indices of the metric tensor. So JK. Yeah. So let's see. This one doesn't. So you have one. I M K and I. Wait.
So J becomes I in that. So it's the same. So J become I for
Yeah, that's just. I mean, all these go. So this one is correct, right? This one is correct. So this is. I just need to use this one to here. So IJ becomes JK, and K becomes M. K becomes M. I I I becomes J. J become K. J become K. And K becomes M, and I
becomes
so this seems correct, right? I think, all right, it seems correct with that. Yeah. Right, I need to contract that. I need to contract that. So K. I and K and they're the same. So I and K are the same. This one, I am. J M become I M K and K M Q I and Q J the same. This is I J I K. Yeah, that's right. Okay, this is correct. And remember, this is still sum. So this I in the sum. This is summing over this superscript with this subscript, and this subscript, and then this subscript, right? With the still sum. Okay, and then once you have that, you can write down the second line is the I N and partial G I N and partial P P. And the idea is that they are everything's similar there, and then the metric tensor are symmetric. So this one is basically this one, and then the M and K and so basically these two are cancel each other because your I. This is I M and M I. You can interchange I M and M I, right? If you change this I M and M I, these two will cancel each other, so, right? So you don't have that. These two, and then this one. Now this one take a little bit of work to do that, and there's an equation in your textbook in chapter 3 that talk. Say chapter 2 talk about that. Let me look that up. This about determinants and then how you solve the determinant and the inverse. This one is fine. So this is just working out. Yeah. The 135, although we skipped chapter. This is from how you write the determinants using what we call the cofactor. And then the inverse also involving the cofactor. And now you take the derivative of a determinant of a matrix A. And then by using all these cofactor, you can show that this equals the determinant A and then sum over all the matrix element. The inverse A J I. Take the derivative of this A. The elements of this matrix capital A, I, G, X. Okay, so this is using this equation and then setting A as the G covariant G. So basically, this one instead of A I J becomes this is because you have a derivative, right? You know, derivative. With respect to one coordinate G, G's of K, that doesn't matter. So that's this becomes X becomes G, Q, that Q is QK, and this G I J. Oh, IJ or I. Doesn't matter, this is the summation, right? And Now the G has the inverse in this contravariant matrix. It becomes G Ji, and that is a sum. And then determinant of A is what we call, well, we define as G vector. Right. And now this one is exactly this one, because remember this we have the M is sum, I is also sum, right? And then we have a derivative, right? So this one, there's a 1/2. So this thing is the determinant of. So this one has a G. This is dg dx, and so we did it divided by G and divided by 1/2. So this is 1/2 of G dg dt. And then you can get rid of this 1/2 by if you take the square root, take the derivative of square root, right? And then because when you take the derivative of so basically you have a G is the square root of it multiplied by the square of it, right? The square of the square root. So when you take a derivative, you get a factor of 2 and multiply the square root and d the square root dq. And then this cancel part one of that, so it becomes the square root d square root d dq. Oh, I'm over time. Okay, so at least finally we get the 4.68. Okay, and once we have that, we can just write it out explicitly because we already have this one. So the divergency is just using this notation. We can square G. G is defined as determinant to this covariant tensor, a covariant metric tensor. Now, then we have this function. Yeah, you can combine. This is just this one, or you can write it. Over time, so I just want to write it. This very new, and then and then finally you can combine the two, with taking the derivative out and get the 4.69, because if you use the distribution rule, you can show that they are the same. No, you don't have that. This is coming from here to here, but you can combine and get to 4.69 by just the derivative rule. Okay, and last time I was in a bit hurry at the end, so I hurry up with the derivation of this divergence, and at the end we use equation in chapter 2. So chapter 2, 2.35. Use this equation for 35. So for any matrix A, if you take a determinant, the derivative of the determinant of A with respect to any variable, then the formula is this determinant of A multiplied by sum of all the elements ij of the inverse of A of the element ji multiplied by the derivative of each element A ij. So this little aij is the elements of the determinant A. Okay, so that's this formula. Have you learned that? Learned about this?
Yeah.
You you learned in linear operator. You learn about that when you understand this. Okay, good. Yeah. So, unfortunately, I didn't know how the other people know about it. I was trying to see if I need to explain this a little bit further. But so now, but then so this basically using the fact that this there are two things. So one is this inverse, which your text will also have a formula, a inverse. The ij component is the so-called cofactor minus and ji is the transport of the cofactor actually. Determine A. So basically, this object is this one. So and then you cancel the determinant. Actually, this is basically the cofactor. That one is attribute. Okay, so yeah, I was trying to explain this formula that I used last time. Yeah. Have you learned about this formula? We used last time. I was asking you whether you learned that before. I told you you have not learned that. Yeah. Do you? I mean, do you understand about or uh, do you know how it come from? How you justify this? No, I'm asking. Have you learned how to divide this? I'm just saying whether I need to explain further
I
to
don't
you.
remember it personally. I don't know if you can hear me.
Someone.
Yeah,
Reasons.
I'm here.
Yeah.
Yeah,
Okay.
I'm here. I don't remember it.
You haven't. Yeah, I was just because I use that. I just don't know whether everyone in the class understand this. So there are two two formulas that involve this so-called cofactor. One is this inverse. We calculate inverse of a matrix by this formula. That is a cofactor. Another is the formula. Another way to calculate the determinant itself. Determinant A is there's another. I think there's another formula in this chapter from earlier. So to that's an alternate formula for calculate determinant. I think one time I showed the other formula involved the Levi-Civita symbol. That is more the fundamental definition. And this one you can say is a property. So you sum over ij. You can sum over a row or sum over a column. That n is the rank of the matrix. So for 3 by 3 is 3 and 4 by 4 is 4. So sum over just one row or one column, and each element multiplied by its cofactor, which is this minus 1 to I plus j factor. Basically, this determines the sign and then the minor matrix. ij.
Why do you have I plus j?
-1 to the power I plus j. So that is basically if I plus j is odd, you get a negative sign. If I plus j is even, you get the positive sign.
The reason why I ask that because I see like the subscript we have ij.
Yeah.
So it means that that's a matrix.
There's a matrix. This a little aij is the elements of the matrix A. Okay, so that's another way to calculate matrix determinant of a matrix. Have you seen that? This probably is more popular way to, right? So let's write down just explicit examples like a 3 by 3. It just it can be anywhere, but like if you have a matrix A11, A12, A13, that's A, right? A21, A22, A23, A31, A32, A33, right? You calculate the determinant. Obviously, you can use what I told you last time. The other time, I used an epsilon ijk, that kind of a way to calculate that. Another way is this formula. Basically, you choose a column or row, and for each element in that row or column, say A11, you multiply by its cofactor, which is the determinant of a submatrix that you cross out the row and column. So for this one, the cofactor, you cross this out, and then the determinant of the rest, which is this time this minus this time that, right? And then multiply by this, and the cofactor involves a sign. So -1 to the ij. This is 1, 1, so it's even, so it's just +1. So this times this times this minus this times this times that, right? Yeah, so that's this element, and then you multiply, plus the other term is this element multiplied by its cofactor, which you cross out the row and column, and calculate the determinant of the rest, which is these 4 elements. Okay, and then you choose the sign. Now this is 1, 2, so it's -1, so it's minus. So minus this times this, right? And plus this times this, whatever, this one, right? And that's the way how you calculate determinant, right? And finally, you multiply the third term, this times the cofactor, which is cos out this row, this column, and then the matrix of this row, right? So that's this formula. You can generalize to any way, right? So that's one way to calculate it. It's not a too efficient way to calculate it, but it's explicit formula. So this one is one way to do that, and I'm trying to justify this one because it involves a little bit of thinking, right? So basically, if you use this formula, combining this times that is just the cofactor, just this one, just this object, and so basically now you're summing all elements. It's not just one row or one column. Sum of all elements. And each element you take a derivative and multiply by its cofactor, basically. Okay, and that might take a little bit of explanation. I don't know whether you can see that right away.
The first one, when the first line there is just like normal way the matrix stuff like when you multiply the inverse multiplied by itself, then it goes away. We have just one. So here, like the way we are trying to, the way you have explained that when we take the determinant of that matrix multiplied by it, it's inverse, like just getting that the sign, the one with the sign.
I don't totally follow your logic, but looks like you are getting it. I don't know whether because this involves a derivative, so it's not too apparent because the most difficult thing is that this sum is over all elements. This is over only one column or one row, any column or one row. And how to use that to this one after you take a derivative is that's another logical step that you might actually, to justify that, you might need a little bit of, I mean, one way to do it in 2 steps. So this is A, right? And if you calculate a determinant of A, basically, no, determinant of A. So let me ask you a question. So how, we just like take a determinant of this one. Doesn't have to be super or maybe high or what is an alternate way to write it out, involving not too many terms. How do we do that? So take a determinant of this object. This is a 3 by 3. So obviously you can write down all the terms. So how many terms in here? So you have 6 terms, right? 3 by 3 matrix, you got 6 terms determined, and each term has 3 factors, right? If it involves product of 3 elements, you can do a derivative and then use the chain rule. So each term will give you 3 terms after you take a derivative using the chain rule. So altogether we'll have 18 terms, right? You can do that, right? That's too many. I just ask you, is there a more compact way to write it out?
And a shortcut, if you write the matrix again, then you can just do the determinant is just the diagonal.
Yeah, you're writing in the matrix. How do you write it? I'm saying now you want to take the derivative, so ddx. How do you write it involving some matrix representation? Yeah, close. Yeah, this is this formula. So I'm just trying to see how you justify this formula. That is an intermediate step, which is kind of useful, also alternately useful. Can you see that how you take the derivative of determinant and write it in more compact way? Doesn't need to transfer. Yeah.
So you find that the derivatives of these terms essentially we're just summing it for that place, like we have made it. So at the end of the day, we are just combining it.
Yeah, at the end of the day, is this I'm asking an intermediate step to justify that. If you write down the intermediate step, probably will justify that. Why you change from sum over one row or one column to sum over all elements. So this is not exactly this one. This is sum over all elements. This is sum over just one row. I'm just asking, this is just an intermediate step to justify that. Okay, so let me just if you cannot see it, there was, I don't know whether I told you that story, but there was a story involving this. So it's not just, if you cannot see it immediately, don't feel bad because another person didn't see that also. So one easy way to do that is when you do a determinant, that you can write it in different terms, each term involving a derivative or of either one row or one column. So each row, so this is involving. Just take the derivative of the first row plus take the derivative of the second row. And then the third one is a lot of writing, even just writing a determinant. And then take the derivative of this third row. Okay, can you see that? Yeah. Now you can see that, right? So it doesn't need too much justification because that's pretty obvious. You can do that. And once you do that, that becomes obvious how you change from summing just one index, one column or one row to sum over all elements. Because now this is just this one, right? You see that all these terms, the derivative of elements involved just appear just one time. So A11 just in here. There's no A11 prime just in here. There's nowhere there's A11 prime. And A11 prime appear only when A11 times its cofactor, which is the determinant of this one. And then this determinant doesn't involve A11 prime anymore. Just this one times this one plus this one times the determinant of a cofactor involving these three elements, and this one multiplied the cofactor, right? So it doesn't appear another time. It only appear when A11 prime multiplied by its cofactor. And similarly for all elements, this element multiplied by the cofactor of the original matrix. So multiply this one multiplied by this four determinant of this four elements, right? So it's appear for all elements, but each element, the derivative of each element appear one time, and the coefficient of that in the derivative is just the cofactor. So it involves summing all elements, the derivative of all elements, multiplied by the cofactor of the original matrix. Right? So that's this formula. Okay. So that's provide you the jump how you get from summing over just one element, one row or one column, to summing over all elements. Okay. So this intermediate style, as I said, involving a story, actually involving I don't know whether you had that. I told many classes about that because when I first attended the PhD program at my institute at Auburn, and so I think the first semester I asked the professor to take me on as an advisor, and then he is Gary Swanson, he wrote some textbook. He liked to write textbooks, so he has a fairly commonly used textbook, Possible Ways. So anyway, he took me on quite right away, and then he has this weekly meeting with me and another student. Actually, that student was second year, but he will go through his research program and all the background material. And he has the habit of redividing everything from the very first equation, redividing what he was doing. He liked that. And he's in his teaching, he's also do that, redividing. I try to learn from him. It's very difficult. It's very time consuming. Every time we talk about something, we keep redividing everything. So that you can say it's a very good habit because mathematics take practice. You keep deriving your learning from you keep reinforcing your skills. But so a few weeks into his derivation, he came up with his program involving solving ODE at higher order, so fourth order, at least fourth order. And there was a fourth determinant of a fourth rank tensor, which are constructed by the solution of this ODE. So, and you will learn that later when we talk about ODE, the Wong-Skin determine what we call the Wong-Skin. And he solved this equation by numerical method. So he constructed this Wong-Skin by his numerical solution, and he found out that that Wong-Skin, the determinant, is a constant. Numerically, you can see from high accuracy that numerical is a constant. But he struggled to prove that and it cannot find an analytical proof. And he showed so as that. And of course, I was not that smart. I didn't know. He just told me that puzzle he had there, and I couldn't figure it out. And after the meeting, I went back to my room and I tried to play with it a little bit. And it's involved exactly this rule. If you use this rule, then you can write down the proof that the determinant ddx is 0. Right away, almost right away. I wrote it up in a page and show it to him the next day. Obviously, he was surprised. He just told me yesterday, and then he struggled with that for quite quite some time, and then like solve it in one page. It's kind of surprising for him, but that's not the most amusing part of the story, because that happened. I mean, you solve your advisor question. That's not that uncommon. You know, it happened quite often in my career also. But what is what is so where I mean so uncommon is that the next week after I show him the derivation, whatever, the next week he keep on going, and then he come up with another puzzle. He has this time involving not 4x4, with a bunch of few of these basically four of these 3x3 matrices that are constructed by the solution of the ODE. And now this time she showed that numerically all four of these matrices satisfy another ODE, which we call the adjoint equation of the ODE. We show that numerically, well, that is something. So a constant is easier to show that these determinants are solution of that ODE. As it take quite some work to show that all four of them are solution. But again, it couldn't show why this is so. And then struggled to prove that. And I told myself, wow, it happened again. And then after I told him, I said, he must be using the same method. And after I told him, he still couldn't figure that out using my method. But I'm not that smart to point it out right away. So after that, I wrote, try it. And then now this time is a little bit more complicated. It's 2 pages. And then write out how to prove that those are the solutions, and I give it to it the next day. And this never happened again in my whole career. two weeks in a row, I solved my advisor puzzle, and then involving something so similar, and then I told him already the first time, he didn't do it, and I mean now I understand a little bit more, because when you are doing teaching and all research, you're busy with all kinds of things. You know, administrative thing, the committee and all that, writing paper, writing proposal, all that. So within a week, we probably didn't go back to the problem and use my method. But if you use just this concept of how you take the derivative, you can show, solve the other problem quite easily. But yeah, apparently didn't do that. Well, it just show that even something as simple as that, it just take a little bit of, if you didn't see it right away, that's common. That's not very surprising. But then once you do that, it has some application. So this is the justification of that. And after you use that and apply to that this A becomes the metric tensor, the covariant metric tensor, and this inverse becomes the contravariant metric tensor, because that's the property of these metric tensors. And so you right away get from 4.66 to 4.67. So you get this just by applying this formula to using the metric tensor. So that's easy. That's straightforward. And then 4.68 is also trivial. It's just separate determinant G to square root of determinant G square, and then work out the derivative, and you get 4.68. And 4.69 is maybe a little bit, you just need to do the distribution rule. So 4.16, also last time I ran out of time, is just went through it too quickly. So you just basically you have this determinant of square root of G. So and sometimes we just use I don't need, because if you define G as the determinant, you don't need to repeat the determinant label and then VK. Right? You just use the distribution rule that that one will involve, take the derivative of that one, which is 1/2 of G. Oh, wait. But this is okay. Take the derivative of that. So that the first one is taking the derivative of that, and then and also reclaim. Okay.
So these are constant.
The Q. This is Q. G is the determinant of the magic tensor. It's usually that actually is a very common label in like the relativity literature, using this little g as the determinant of the covariant magic tensor. Okay, and then the second term is this take a derivative of that one. So, and this one you 4.69, and then you divide it by square root of g. So basically cancel this. Okay, and this two term is just it's just the two terms in 4.65. Right? After you substitute the Christoffel symbol in 4.68 into 4.65, then you get that. Right? So so this 4.69 is just writing it in a more compact way, combining the two terms in the single term using that. All right, so
What happened to the V of k in the second term?
yeah, there's nothing happened. It's just I forget. All right, so that, I mean, you compare with 4.65, so that's fine. Right. Okay, and so that's divergence. And the next equation is directly using the next equation is not as complicated because we already have the divergence, the Laplacian of psi of a scalar. Now it's just divergence of gradient of psi, right? The divergence we use this formula, or the formula 4.69, so that 1 equals square root of g also has the q k, and then square root of g multiplied by the vector component. But the vector component is the gradient of the scalar, and it's a contravariant. When you take the scalar, when you take the gradient, it becomes a covariance, and because your partial qk in the denominator become covariant, and so you need to bring it up to contravariance. So you multiply it by metric tensor, contravariant metric tensor. Okay. I'll just also qi, right? That's the gradient, and change covariant to contravariant by this metric tensor. That's the VK. That's the formula. Laplacian. So that's a little bit trivial. All right, up here. So the next thing is I mean, these are general formula, but if you go back to the special case of a curvilinear coordinate system, so that has the property that all the unit vectors, all the basis vectors are orthogonal to each other, and we usually have a notation for curvilinear. So those are, and remember when we derive this using this formulation, the basis vector we are not normalized. So we the basis vector, the covariant basis defined as partial xj, right, partial qi. The the potassium unit vector, right? We use that to define this epsilon. But this is usually not normalized, right? So to normalize that, we usually just introduce the h factor, hi, and now that we have a little bit of whatever the label, how you define. We already use of E sub I. So this is also a unit vector, but let's just write it as Q. Right. This is the unit vector corresponding to this Qi coordinate, but this is normalized. So this is has a unit name, and you multiply by this vector hi, right? And so this, and they are orthogonals, or like all these basis vectors. These unit vectors are orthogonal for the curvilinear system. Okay, and using that, obviously the metric tensor becomes this. It originally is EI, epsilon I times dot into epsilon j, right? So obviously that becomes HI, HJ times EQI dot into EQJ, right? And that's just a conical delta. Conical delta Q, but that's a QI, QJ. Yeah, QI, QJ. This the label is a little bit strange, but I mean, let's just okay. The label, just talk about the elements. Obviously, the off-diagonal terms are all zero because these are orthogonal. So only non-zeros are the diagonal terms, and diagonal terms as I equals to j. So it's so this is like if you want to write like HR squared and delta IJ. Okay. It's not sum. There's no sum. No sum. Right? It just means that the elements are given by this one. So for I equals to I, your so I equals to 1, your h1 square, right? The G11 element is h1 square, like likewise. G22 is G2 square, h2 square, right? And all the off diagonal terms are 0. Okay, so obviously because of that, the G will be just h1 square, or h1, h2, h3, or whatever the number of rank square, right? And these H factor you can look up I mean, your textbook in chapter 3 has a discussion of the specific case of the new coordinate, spherical coordinate, and has the derivation of all these H factors for different components. You can look that up, and so that's actually quite trivial to derive because you just use this definition and do a derivative and then determine what the H factor is. So that's straightforward. It's not trivial, but it's straightforward. Okay, and once you have that, so you can use that for either the Laplacian that involve a g here, involve a g. So you can change all this square root of g into just h1 times h2 times h2. Okay, so that becomes the divergence formula or the Laplacian formula for curvilinear coordinate system. Okay, so that's another way to look at it more specifically. And those formulas, you probably have seen it before when you learn all this generalized curvilinear system or vector calculus. Okay, and the curl, last time is the curl, and that's popular. I think that in one homework problem, the curl is, now instead of a curl, is actually writing it as in component form. This is a covariant. Q. Minus 3j. just make it a anti-symmetric object. So it just interchange ij and change the sign for the second chain. Okay? And that involving just ordinary derivative, but because of this subtraction of the anti-symmetric term, you actually can prove that this one is exactly the same as the covariant derivative in the sense that it's the I component, and then the I component of the covariant derivative of Vj minus Vj. That involves the covariant derivative of a covariant coordinate, which is slightly different from the formula. And actually, your textbook has the formula. So we talk about the covariant derivative of the contrarian coordinate is 4.57, and correspondingly, you can divide 4.58 for this object. So that you can use this formula to use that formula 4.58 to show that these two are the same, because whatever the crystal Feld symbol involving in these two terms cancel each other. So once you cancel, you just have this ordinary derivative. So that is how you curl. So the curl is in a sense is easier, because you involve just the ordinary derivative without all this crystal Feld symbol. Okay. I think that's the end of this 4.3.